Hi, this is an example problem from Chapter 18 on how to calculate the net electrostatic force in two dimensions. Pause for a moment and read the question. So this question's got two parts, A and B. In the first part, we're going to see how we need to use vector addition in two dimensions to be able to calculate the net force on charge Q3 due to its interaction with the other two charges. In part B, we're going to understand how that net force on Q3 affects the acceleration of Q3 if it's allowed to move. So we assume, as usual, we've got these three charges, they're fixed in place, and we want to try to visualize this problem. We see which charges are plus or minus, which is great. We see there's a separation here between various charges. In this case, D is given as 5 centimeters, but we want to remember that this is really a distance that we need to convert into meters. So this would be 0.5 meters. And we're also interested in the distance between charge Q1 and Q3 because those two are interacting as well. And so if we go ahead and draw a straight line between those, that'll help us see that distance between the two. And if we think of the distance between these two exactly, well, we know that that's actually the bisector of a square. And so it turns out that if we know what the side length of this square is, then we can go ahead and figure out what the length of that is. It's just equal to root 2 multiplied by 0.05 meters. And that turns out to just be from straight geometry, so we know that as well. Now, I want to go ahead and identify these because we're going to use Coulomb's law to do this. So if I look at Coulomb's law here, I've written it for the magnitude of force interaction between charges 3 and 2. We see that distance there, R32, it's in the denominator, and we have the charge values, take their magnitudes, put those in the numerator, we can calculate the magnitude of that force. So that's what we're going to start with. And we're going to similarly do this for the other set of charge interactions. So in this case, we'll also do one here, charge 3 on 1. So I've got the two Coulomb's law formulas we want. I've fixed up the notation to understand what's what. Let me pause for a moment. I'm going to just put in all the numbers and we'll calculate these. So I've gone ahead and I've written in all the numbers here. All the charge values had the same magnitude, 2 microcoulombs, so that was easy. And we just had to go in and put the different values for the distances here. And in fact, I'm missing one thing. This should be squared. And in fact, when we square this, you can see that this root 2 is going to get squared. It's going to become a 2. So we expect the lower one to be half the size as the upper one. And it is. We put it into our calculator and we end up getting, for the top one here, we got 14.4 newtons. And for F on 3 by 1, the further one, it's going to be reduced. It's going to be 7.2 newtons. And let's go ahead and draw these two vectors because these are the magnitudes, but we got to get the directions. So for F on 3 by 2, I'm going to focus on charge Q2, and I'm going to look at charge Q3, and I'm going to say, okay, along this line connecting the 2, is 2 going to push 3 away or attract it? Well, they're the same charge, so they're going to repel. And so I've got a force like this, which is going to be acting on 3 due to 2. And the length of that arrow, 14.4 newtons. Now, for the other one, look at the line between Q1 and Q3. Is Q1 going to be attracting Q3 or pushing it away? It's going to attract it because they're opposite. And so we can go ahead and draw a vector like this. And this one is half the length, F on 3 by 1, because its magnitude, the length of that arrow is 7.2 newtons. Now at this point, I need to go ahead and do vector addition to figure out the components of these vectors before I can add them. So let's go ahead and copy this and make a nice little picture of this. All right, so we need to add these two vectors in order to get the net electric force vector on charge 3 due to all the forces that are on it, these two forces. So I've drawn a table which is going to be extremely useful to help us organize our components and do the vector addition. And the forces, actually we're going to go ahead and separate these and plot them in their own x and y axes so that we can simply identify the vector components of these using our trigonometry. All right, so I've kind of blown up these pictures and put some x and y coordinate systems on there, focus at each vector individually to make it simple. Let's start with the force vector F on 3 by 2, the green one. That's a simple one to figure out the components because that vector lies completely along the x-axis. That means that the y component is 0, and that the x component, it's points in the positive direction, and it's the entire magnitude. All 14.4 newtons point in that direction. Now for the other vector, we're going to need to go ahead and take that magnitude, 7.2 newtons. We're going to have to break it down into components along the y direction. We call this, let's just call this the y component here. And over here, there's our x component, right? Now, for this problem, I know that this is a perfect diagonal of a square, and so I know that this is equal to 45 degrees, this angle. And so I can figure out the components here. The way I do this is I'm going to go ahead and choose my x component here. So one way to write this is f31x, and the y component is f31y. And the way that we typically do that is we just write the magnitude first, right? So what is the length of the hypotenuse, the magnitude? 7.2 newtons. And now I need to go ahead and look for just the x component here. And I need to use a trig function. Remember sine and cosine? X is opposite of 45. That's sine. So we're going to use sine of 45 degrees. And I also need to look at one more thing. So there's really 3 steps to this problem here that we could possibly be doing. And that is, I've got the 2 steps, the magnitude and the angle, but does the x-axis point plus or minus? Well, it's in this direction, right? So that's negative x. So I got to put a minus sign in there by hand, and then we'll calculate that. Now for the y component, I see it points up, so I'm going to write positive. Next thing I do, I'm going to write the total magnitude, 7.2 newtons, and then I can see that the y component, that is 45 degrees. It's touching the y-axis right here. That means it's adjacent. That's cosine. And so I'm going to write down here cosine 45 degrees. Now notice I chose this particular triangle like this to do my components. You could have chosen this one, but the key thing to remember here is when you're picking your angles, and you're using the trigonometry, look at the triangle you chose and do sine is opposite over hypotenuse, cosine is adjacent, right? So that's the key thing to remember. Let's put these into the calculator, see what we get. So this comes out to negative 5.09 newtons. And the one on the bottom, because 45 degree angles have the same values for sine and cosine, positive 5.09 newtons. And I'm going to put those into my table now. So for F31x, negative 5.09 newtons, and F31y, positive 5.09 newtons. And now we're going to add. This one's simple, to add the y components, the two points in the column there, add a 0 to it, and you still end up with that number. And the other one we have 9.31 newtons. So in a sense, we figured out the components, the net electric force components, F3x, it's equal to 9.31 newtons, and F3y, it's equal to 5.09 newtons. However, in this problem, we want to remember that they're asking us calculate the electrostatic force in terms of the magnitude and the direction counterclockwise from the plus x-axis. So we got one more thing to do. We need to plot that vector that we just determined, F3, and figure those things that we set out. So we need to go ahead and use our vector tools to figure out the magnitude and angle. So I'm going to plot this in an xy coordinate system. I know this is positive, x and y. It's a first quadrant vector, and I need to find the point in the plane that corresponds to those 2 points. So for the x-axis, we're over here at 9.31 newtons. And for the y-axis, we're over at 5.09 newtons. And that marks the point in the plane. That's the tip of our arrow. So we can go ahead and draw our vector straight there, and that is the vector F, the net electrostatic force on charge 3. And we need to go ahead and figure out, based on these values here, let's go ahead and draw in the components. So there is our F3x, of course, there it is. We can move that over there if we want. And I'm going to put over here our F3y. Of course, that's the same thing here. And to calculate the magnitude F3, the hypotenuse, remember that we use the Pythagorean theorem because it's the hypotenuse of a triangle. So that's going to be the x component squared plus the y component squared. Then we take the square root of the whole thing there. And that comes out to, that's a 10.6 newtons. There's our magnitude. Now to get the angle, counterclockwise from the plus x-axis. So here we've got 0 degrees. Up here's 90 degrees. Here's 180. And we're going to start here and go counterclockwise till we get to the vector. That's the angle we're looking for. We can see that that angle is actually going to be tangent we could use. But if we want to get the angle, remember, if you know the sides, you want to get the angle, you have to use the tanverse inverse function. So opposite, right? That angle opposite is the y component. 5.09 newtons divided by the adjacent part, 9.31 newtons. Of course, the newtons cancel. And if we put that into our calculator, we'll calculate 28.7 degrees. So there's the answers for part A. Now, if we go back to these vectors, if we want, we can go ahead and do vector addition here graphically, and we can see that if we draw the green arrow and then we put the purple arrow to it, let me scale that a little bit better here. And if I draw starting from the first spot on the green arrow to the tip of the purple arrow, we can see that, that's how the graphical vector addition looks. All right, let's go take a look here at part B for this problem. Part B says, if Q3 has a mass of m3 equals 2.5 grams and is released from rest, what will be its acceleration? Well, in this case, we know that we have the force that acts on Q3, and that's going to cause it to accelerate. Now, in this problem, we assume that that's the net force, F on 3. In other words, the sum of all the forces that act on 3, it's just this electric force, the net electric force on 3. And we're going to use Newton's second law because that's how you calculate the acceleration. So the acceleration, that's equal to, you got to take the force, that's what impels acceleration, drives it, right? You divide by the mass of the object, the mass of the charge here. Call this one m3, right? For this problem, we know that we could do a vector equation. However, if we want to just know the magnitude of the acceleration, we can go ahead and take the magnitude of both of these. The mass is always positive. I don't need to take the magnitude of that. And so the magnitude of acceleration, that's just going to be the magnitude F3, right? Which is, this is the same thing here as this. Just two ways to write the same thing. And we're going to divide by the mass M3. So we know that this is a 10.6 newtons. And I just looked up at the top that the mass of charge 3, it's 2.5 grams. That's the inertia resisting acceleration, right? But we actually need to go ahead and convert that to kilograms, right? So that we got to move the decimal place over by 3 to make it smaller. That's the SI unit. And when we calculate that, we come up with 4,240. And what are the units of acceleration? It should be meters per second squared. And we can check that out because what is a newton? A newton is equal to a kilogram meter per second squared. And then we're dividing by a kilogram, right? So if we do this with the units, we'll see the kilograms cancel and we're left with meters per second squared as we expect. And so that's the magnitude of the acceleration. Now, based on Newton's second law, this equation, right, that relates the acceleration to the net force and the inertia of the mass, since these two vectors are proportional to one another, they always point in the same direction. So if we wanted to state the angle, what direction is the acceleration in? Well, we don't have to recalculate. We know it points in the same direction as the net force. So we could also say this is 28.7 degrees counterclockwise from the plus x axis. And in fact, over here, I should have specified this guy here as being from plus x axis. So there we go.